We have 5 capacitors connected in this specific pattern. All the capacitance values are given, and the potential difference between points A and B is also given, and it's equal to 35 volts. First, we'd like to find the equivalent capacitance of the whole system. Now, there are two different ways of connecting capacitors, the series connection and the parallel connection. And the question is, which one is this? Are these capacitors connected in series or in parallel, right? Because there's a different formula for each. Now, it turns out this is a combination of both parallel and series connections. So in a case like this, we start by looking for a subgroup of capacitors for which we can identify a single type of connection. Now, if you look at the 3 capacitors in the middle, those 3 are connected in series. Now, how do I know that? I can see that they're all on the same path. They're along the same single path. So that means they are connected in series. So I can combine these 3 by applying the series connection formula. So let's go ahead and do that. In the series formula, we add the reciprocals of the capacitance values, and then we invert the final result to get the equivalent capacitance. And when I do the calculation, here's what I get for the equivalent capacitance of the middle group, 6.17 nanofarads. Because this is an intermediate calculation, I'm keeping one extra significant figure. Now let's go ahead and redraw the group of capacitors. Here I have the picture redrawn with the middle group replaced with a single capacitor having the equivalent capacitance value. Now when we look at this group, we see that all 3 capacitors are connected in parallel. So let's go ahead and apply the parallel connection formula to this group of capacitors. To find the equivalent capacitance in a parallel connection, we simply add all the capacitance values. And here's what we get when we do that, 18.9 nanofarads. So the original group of capacitors is equivalent to having a single capacitor with capacitance 18.9 nanofarads between points A and B. And the voltage between points A and B is 35 volts. Next, we'd like to calculate the total charge stored in the system. Again, we're going to use the equivalent capacitance because whatever this capacitor can store with the given voltage, the entire system will be able to store the same amount of charge with the given voltage. The defining formula for capacitance is charge divided by voltage. Now, in the case of the equivalent capacitance, it's going to be equal to total charge, again divided by the applied voltage across the terminals of the entire system. Isolating Q total and substituting the numerical values, I get total charge equals 660 nanocoulombs. Here I kept 2 significant figures in my final answer. What if I wanted to calculate the charge stored in the capacitor at the bottom, the one with capacitance equal to 4.6 nanofarads? How would I calculate that? Now, we don't need to calculate anything for this one. We can directly calculate this value without knowing the equivalent capacitance at all. Why? Because this 4.6 nanofarad capacitor is in between the potential points A and B, right? So the potential across this single capacitor is also equal to 35 volts. So we can directly apply the capacitance formula to calculate the charge stored in this single capacitor, like so. We simply multiply capacitance times voltage. And I get Q equals 160 nanocoulombs, keeping 2 significant figures. Now again, how come I was able to do that? Well, this is potential point A, and along this wire, all these points are just A. As long as you don't go across any circuit element in between, all these points are the same potential point, point A. On the other hand, that's on the left hand side, right? On the right hand side, we have point B, and this is also point B, this point B. All of these points, until you get to the capacitor, are all the same potential point, point B. So 4.6 nanofarad capacitor is between potential points A and B, so the potential across this capacitor is equal to the 35 volts. And the same is also true for the capacitor at the top, the 8.1 nanofarad capacitor. That one is also between potential points A and B. So if you want to calculate the charge stored by this capacitor, again you would use the same voltage value, 35 volts.